This starts Chapter 2, Section 1. We are going to get through this section today. And we finally get into, all of Chapter 1 should have been basically a refresher for you. Chapter 2, we're finally going to get into one-dimensional motion. You probably covered several things in one-dimensional motion back when you had physical science with Coach Layton. But as of right now, one-dimensional motion, and we'll proceed on. From this point on, we're going to start introducing equations, and those equations get abundant quickly. So just be prepared. So one-dimensional motion, it is talking about motion in one direction. We will, before it's over with, get into two-dimensional motion, and all of this is based on your frame of reference, and we'll talk about what a frame of reference is and who or what can be a frame of reference.
A train moves from one station to another on an Earth that is rotating and revolving, and in a solar system and galaxy that are both moving. A frame of reference is defined to simplify the description of the train's motion. The motion of this gecko can be described by imagining a meter stick placed under the gecko to define a frame of reference. Observers in different frames of references will see the motion of objects differently. The red dot in this picture is a stunt dummy dropped from the plane. From an observer in the frame of reference of the moving plane, the dummy appears to drop straight down and splash in the water. And from an observer in a stationary frame of reference on the ground, the dummy appears to fall in a curved path.
So again, when we were looking at that video, it did talk about frame of reference. You could see a couple different things. It said if your frame of reference was if you were in the plane itself, and you were looking down from the plane and you dropped your package, what did it look like the motion was of the package? It looked like it was just going straight down. But it said if you are an observer and you're watching the plane go by over here, what does it look like the package is doing? It looks like a curve. So as it's falling, it's going to look like this. So it looks like a curve. It's given us some more information. Displacement means change in position. The SI unit we're going to use is meter. The reason why we use that is because also whenever we go into derived units and we start putting different units together, meter is going to be the base for that. It's not saying that information won't be given in centimeters or millimeters or kilometers, but they will have to be changed over to meters before in general you do your work. And again, anytime you see that delta sign, delta always means a difference, so it's final minus initial. Delta is always final minus initial. In this case, they're using the X. X is for displacement, and it could be delta T for temperature. It's still final minus initial. It could be delta little t for time. It's still final time minus initial time. Always final minus initial. In these examples up here, it's showing you positive and negative displacements. Depending on which direction you're going, direction has a lot to do with what we consider to be positive or negative. As far as positive directions, give me some words you might use to describe what someone would assume is a positive direction. Forward. Up.
Not backwards.
What about north?
Yes.
Okay. We're going to use the quadrant system a lot. And when we're using that quadrant system as far as north, south, east, maybe you can't see the east part, but east and west, on the quadrant system, what's considered positive? North and east. So negative is going to be west or south. And then what are some other negative connotations? Down and backwards. So several words because you're going to be given tons of word problems, and you've got to look for some of those key words. Even though something doesn't give you a number, it won't say -10, but it might say 10 meters south, and that is going to include to you, okay, maybe that's a negative type direction. So there's some examples up here. They're using left and right, but again, it's always final minus initial, and you can tell the positives and negatives. Even though it says -60 centimeters, it's not that it went below 0. The negative is just showing direction. And you will see that very often where negative simply means it's indicating a direction. So now we have another equation. You've got your velocity here. We had delta x earlier, which was your displacement. So as you're maybe keeping up with an area that has all of your equations in one spot. Okay. Delta x, that has something to do with your change in distance. And the distance could be in any direction. This v right here, that's an average. That's delta x over delta t. So the v here is velocity, and the units for velocity are meters per second. Meters per second.
Moves from point X sub I at time t sub I to point X sub F at time t sub F in the amount of time shown by the clock. The average velocity of the car is the displacement divided by the change in time. Since the car is traveling to the right, the sign of the displacement is positive and is equal to X sub F minus X sub I. The time interval is always positive and is equal to the final time minus the initial or starting time.
So make a note, your change in time is always positive. Remember, we can't go back in time.
The average velocity can be a positive or negative value because the displacement can be either a positive or negative value.
And again, it can be negative because the direction, if it has a negative connotation to it.
Even though the motions of these two cars differ, at time t sub f, they have the same average velocity because they underwent equal displacements in the same amount of time.
Okay, some more definitions here. We've already talked about velocity. Comparing velocity and speed, we're going to use the same symbol, that lowercase v, for both velocity and speed, but one is magnitude only, the other is magnitude and direction. So even though numerically velocity and speed for a given problem would be exactly the same, velocity, you would show direction along with that. It is the same equation, okay? For speed, it's distance traveled over the time interval. For velocity, it's a change in distance traveled over a change in time. So it's basically the same equation. Just again, with velocity, you would indicate direction in your answer.
So could speed not be negative?
Well, no, typically we don't give a negative there because we're not really concerned with what direction you're going. And this one right here, it's showing you a position time graph. We looked at graphs in the last chapter. Depending on the direction of your line or the slope that it takes on can mean several different things. Notice on this one, if it's a position versus time graph, position is on the y-axis, time is on the x-axis. Like I said, rarely will you see time on the y-axis. But if you look at the three different objects, for object 1, it says it's got a positive velocity. Object 2 has 0 velocity. Why do they say 0 velocity? If I'm looking at object number 2 right here, right, the line is flat, okay? So time is still increasing, but position, it's staying in the same position. Notice it says 0 velocity. It doesn't mean that your car, say it's your car is not moving. It's just the car could be constantly going 60 miles per hour. Okay? And it's staying at that speed. And then object number 3, it has a negative velocity. So make sure you show those 3. It's the bottom 3, the object 1, 2, and 3. They're more important. As you can see from this is showing you instantaneous velocity. I know you've done instantaneous points in math, and so for instantaneous velocity, you pick a point along your charted line. It can be any point because you just want to know the velocity at that particular instance in time. So for the one that they've picked right here, it looks like this point right along the line, the dotted line, y'all know that that is a tangent line. So at that tangent line, you can now find the slope of your tangent line. You will pick the XY coordinates here, the XY coordinates here, and again, it'll be delta Y over delta X, and you can find your velocity there. So final minus initial, get your velocity. So here, I have skipped over to section 3 out of this chapter. We are not going to actually cover section 3. It's about free fall, but I do want you to see this video about free fall to help you with your homework.
Let's toss a ball into the air and think about its velocity and acceleration as it travels. When the ball is first tossed into the air, it is moving quickly upwards. It slows, then changes directions, and speeds up again on the way down. Let's look at this again and focus on the velocity. Suppose the initial upwards velocity is 20 meters per second. As the ball travels upwards, the velocity slows. Let's freeze the motion at the top. At this point, the ball is no longer traveling upwards, so it does not have a positive velocity. However, it has not yet started moving downwards, so it cannot have a negative velocity either. The ball must therefore have a velocity of 0. Next, the ball starts to descend and gains speed as it travels. Let's throw the ball one more time and graph its velocity as a function of time. As you can see, the velocity changes smoothly from upwards, positive, to downwards, negative. Remember that acceleration is the slope of the graph of velocity versus time. You can see that the velocity graph has a constant negative slope. This slope is the acceleration due to gravity, negative 9.8 meters per second squared. The ball has this same acceleration at all times, even as its velocity is positive, then briefly 0, then negative.
This is something that you need to know as far as the acceleration itself. Acceleration due to gravity, we call that AG, is the 9.81 meters per second squared. That is something that you will need to memorize. If we're looking at the first part of this graph, you can see that that is decreasing. And that is the upward slope of the ball in the first part of that graph. And if we look at the second part of the graph, this is actually the velocity becoming negative 10 and negative 20. The velocity of the ball is increasing. It's just that it's increasing in a negative direction because the ball is now moving down at that point. So looking at the whole line, it does show you the curve up, the curve down. And at the point right here in the middle, if we look at it, notice that the velocity is 0. That is when the ball hit the top of its arc, came to a stop, and then started moving down.